Greetings. In this video we will talk about how to find the distance between two parallel lines like this in 3D space. And there's actually a particular thing to take into account as compared to doing the same thing with two lines that are not parallel in 3D, skew lines that also don't intersect but are also not on the same plane. Where parallel lines basically in 3D, if they do not intersect, they are two different lines and they're on the same plane, they must be parallel, which is this case. So just to first of all talk about a little about the two lines we have. Well, I can of course kind of draw it. Let's say this is the line 1, this is the line 2, drew them parallel to show they are parallel. And why are they parallel? We can see in the expression for both of them, L1 and L2 are defined using a point each and then a vector each. And because they're parallel, they have the same direction vector. The vector is namely 2, 3, 1. We see for L1 it's A multiplied by 2, 3, 1. For L2 it's B multiplied by 2, 3, 1. And the A and the B are just scalars. And what the line does is it is infinitely long throughout space. And that vector gives it direction. So however many times we add that vector, we can just move along that line. And the point, which is this column in both cases, is a point that the line necessarily goes through, and it is a particular point on the line actually. If we set A here or respectively B here at equal to 0, basically the coordinate of the point of that point will be basically what this left column is for each of them. And if we want to join all the other points, well, we first of all take this point and then we add however many times the 2, 3, 1 vector. And in the L2 respectively again the same thing. We know that definitely it goes through this point, but then we can subtract or add however many times the 2, 3, 1 vector we want. How the additional vector subtraction works, well, that's basically required to know to actually be able to work with it like this. And what I want to comment in this one on is basically a way, or to show a way how to find the distance between lines when these vectors are same. Because there's a different approach to be used when we want to approach it through construction of linear equations and avoid using projection, for example, to find the distance, the shortest distance between these parallel lines when they are parallel on one plane 3D as compared to skew lines. And the reason might or might not be apparent throughout our working, and if it is, I might refer to that reason. But in any case, let's first consider what this means. So I've kind of explained what L1 and L2 are defined as. They're in so-called vector form. That means for each of them we have a point they go through. That's the first column, and then that ladder that just says whatever real number we want to multiply this vector by and add it to that point that the line goes through. Then we can generate all the other points. So if I talk about some point A, let me talk about some general point A or let's say let's talk about some point B, and let's say this point B is on L2. So what I'm doing is I will now use the information we have for line 2 and I will just try to re-express it, because this re-expression will actually help us with the logic of how to continue. So if we have some point on L2, it will satisfy these things. Its x-coordinate will be equal to the x-coordinate of the point that the line 2 goes through, according to its vector definition that we see right here. And then added to it will be b times the first coordinate of the vector, of the direction vector. So we have 2 plus 2b. So every point B, every point capital B on line 2 will have the x-coordinate defined by the parameter with b inside it, namely 2 plus 2b. Every point y, every coordinate y of a particular point, depending on what we plug in for b, again, in respect to b, will be 5 plus 3b. And every point z, now we just look at the third row of both the point and the vector there, is going to be 7 plus 1b. So that means that whatever b we choose, let's say 1, we plug in for all these three things and we get a particular, again, free entry point and that point will be a point B, and it will be on L2 because it will just follow what the vector equation for the line said. So we have this. Now I can draw it here. So on line 2 we have some point B like that, and that is useful for a reason, because what we got here is basically some point B, and what we want is the shortest distance between the lines. That means that there's going to be some vector that connects B to some other point on L1 such that this connecting vector is parallel to both of them. Only when it is parallel like this, it is the shortest distance between these two parallel lines. You could also do kind of a more diagonal version of it, like this, but that's not the distance between the lines. That's just some random connection of 2 points on the lines that not necessarily shows the shortest distance. So we wanna have the shortest distance, which is B to some point that is straight on the opposite side when we look perpendicularly towards the other line, from L2 to L1. So how do we get that? Well, the technique I will use is basically I will make use of this part that we got here, and secondly I will talk about some concrete point on line 1. But the point here will be that for line 2 we will keep the point general. That means, yes, we will use this part, which is necessarily like the point part of the vector equation of the line, and then we leave this parallel option. That means we can add some when we plug in for B something that's not 0, we get some options here. So I will also keep this part. But for A on line 1, so this is a new idea here, point A on line 1, I will just use not to have the parameter A in that equation in a second that I will construct. I will just use this base point here, just the 0, 3, 1. I will not use the 2, 3, 1 again, because we already have that vector once thanks to B. So we just need a point on L1. So what I'll be doing basically is I will create a vector AB, where A and B are not the same idea in either of these lines. In general, one could talk about them as the same idea if I also define the capital A on L1 in the way that I also added the parametric vector thing there. But because we already had the same vector, this part, the 2, 3, 1, because of B on L2, then I would be repeating the information. And actually it would cause problems. In the end, in a second, we'll progress a bit with this computation, and we would get at the end one equation with 2 unknowns. So we want one equation with 1 unknown, and therefore this is the reason why I'm doing this. Maybe it will be more visible why it is so when you go through this video another time, or when you do it yourself on paper. You might try to define the point A just like we did it with B, in such a way that x will be 2 plus 2, 0 plus 2a, y will be 3 plus 3a, z will be 1 plus a. And then you will find out, if you continue the way we will now continue with the calculation, that you might get into a trouble, but there will be one equation but 2 unknowns in it. But we will do it in a way that we have one equation, 1 unknown, and thereby directly we get the result. We approach the result very quickly. So how do we continue now? Well, I want to construct some vector AB, and I want this vector AB to be perpendicular to the direction of both of these lines. But both of these lines have the same direction, namely this vector, the 2, 3, 1. So whatever this common vector for these two parallel lines is, I want it to be perpendicular to our AB here. So 2, 3, 1 is perpendicular to it. And there is some property, and this property is tied to the dot product. So when we take the dot product of two things and it's equal to 0, means these two things are perpendicular, and this very property we will now use. So I will do AB must be perpendicular with 2, 3, 1. AB as a particular point on L2 with a concrete point on A1 or on L1 are connected. this creates a vector which is parameterized by only the b parameter of L2, because the parameter of L1 we left out, because from L1 we just chose this point. Okay, I could plug in a concrete thing for A and choose another concrete point for L1. That means I could do 0, 3, 1 and then add 2, 3, 1 to it, and again just enumerate it and as a single column use that point. But I chose the easiest way, just this point that we are given here anyway. And I want to connect it with B, which we nevertheless have defined like this, and create a vector out of it and make that vector perpendicular to 2, 3, 1. So how we now continue with this calculation is as follows. We'll first of all get rid of this right in here and simply continue with the calculation. So I will construct the vector AB. So hereby AB will be equal to subtraction of B from A. B is a parameterized point. It can be anything depending on what B is set to here. But in any case, we can still write it as a free entry vector. So it will be AB for X will be 2 plus 2B minus what it is for A. And in A it is, namely, we chose A to be this concretely. We chose A to basically chose A to be on L1. And we chose it to be that 0, 3, 1, which you can find in the default vector form that we have on the left top corner. So minus 0 here. And then for the y, it's 5 plus 3b minus the y, which is for a 3. And for z, the final one, 7 plus b minus the z part of a, which is 1. So what is this equal to? We can further simplify it. And I will now delete this thing because we've used it and there's no more space to work with. And so let's keep in mind the important things, and that is namely that A and B, although they might seem like analogy, once I've done A, then B is the same idea, or when I did B, A is the same idea. It could be, but now for this example, I define it in a different way, such that B is still parameterized. B can be many different points on L2, but A is only that one chosen point on L1. And the reason I did it is because eventually, now I will do a cross product. And after that cross product, there will appear an equation, and this equation must have one unknown, not two. If I parameterized it for L1 as well, we would have the A there as well, therefore two unknowns in one equation. So I will further simplify AB now. I will further simplify AB now and basically make us able to thereby finalize this calculation. So I want to do a dot product AB with the directional vector of these two lines, and the directional vector of these two lines is 2, 3, 1, and I want it to equal to 0. So this is a very important part. This is probably the most fundamental part. Now I will plug in the AB there. So 2 plus 2b, simplifying it doesn't change. Again, free entry vector, I just have to simplify all of it. Then we have 5 plus 3b minus 3, so 2 plus 3b, and 7 plus b minus 1, 6 plus 1b. So I delete again this part because there's no more space, and we can expand it into an equation. So what this will create for a situation is we will be able to now dot it and enumerate everything, just like was in the line above, still the same. But now I replace the AB with actually vector, and it's parameterized only in B. And now the result of a dot product will be a single equation. On the left side, a single expression, no vector. It will be basically a scalar expression, or a combination of numbers and B, but like a linear combination of B's. And then on the right side we have 0. So how do we do it? Well, dot product, again, a knowledge required for this before going into this topic. Dotting the individual, multiplying the individual entries that correspond and adding them. So it's 2 times 2 plus 2b plus 3 times 2 plus 3b plus 6 plus b times 1, all of that equaling 0, and we have this 4 plus 4b plus 6 plus 9b plus 6 plus b equals 0. It means b equals minus 16 over 14, meaning minus 8 over 7. And now we can return to the initial vector, to the vector AB. So the vector AB denoted the distance between the two lines. And this brings us back to the beginning of the calculation, to the whole motive, to the whole goal of this process. So we want to get the distance between the lines. And B was parameterized in respect to B, and A was a fixed point on L1, where B was on L2. And just to remind the vector what it was, we had it written before, but it got deleted in the meantime. It basically was 2 plus 2b minus 0, so 2 plus 2b for x. For y was 5 plus 3b minus 3. So it was 2 plus 3b, and then 6 plus b for z. And now what we want to do is, we know that b is minus 8 over 7. So what we do is, we put the minus 8 over 7 right inside all these 3b's here. And what that creates is basically a free entry enumerated vector. And to get the distance, denoted as small d usually, as we see right here, we take the magnitude of this AB vector. So we got the vector which precisely is perpendicular to both of the lines, because it was in cross product with their direction equal to 0. And now this vector that denotes the shortest distance between the lines, or the shortest distance from a fixed point on L1 to a parameterized point on L2, but it was parameterized so that we could actually get a concrete value for B, and that the parameter would be replaced by a number, and everything now got enumerated. Now basically, because every point, every chosen point on one line can get the shortest distance vector to the other side in this way. So if we chose now this A to be fixed, then we found the particular B that is right on the opposite side, so that it's perpendicular. This vector that connects the lines is perpendicular to them. Now it's the shortest distance. Now that we have this distance vector, we can take the magnitude of it to get its direct enumerated length. And how we do it is, we take the 3 entries that it has, square them, and that gets added. And the result of this will be the result of this. And how do we do it? Well, yes, we will get enumerated vector AB here, and then the x, y, and z entries all get squared. So you can finish this yourself. There's not much space left to do it now here like this, but you can finish this as an exercise and get the actual value for D.